Yeah, don't you remember you let me out?
Did
You
we begin?
gave me a pass and everything, but I have to be honest, he jumped me, and I...
Bend over.
I don't trust this.
Here's the stamp. Let me back.
You're an electrical engineer, you don't trust the microphone?
I just, and we just learned again, thanks to heaven, the keg part.
Okay.
We're going.
That's not bad.
So, hi everybody. I'm glad to introduce your wrestler. He actually happens to be my PhD advisor. So if you don't like the way I teach, it's because of him. Okay, so just a bit of background. He received his undergraduate and master's degrees from the Technion in Israel. I actually also got my undergraduate and master's degrees there, so it could be that. So it might not be him. So that's probably his excuse. His PhD is from Stanford. All of those degrees are in electrical engineering. He's a professor of departments of electrical and computer engineering and bioengineering, and both of them are located in the Coordinated Science Lab at the University of Illinois at Urbana-Champaign. He's also the president and chief technology officer at InstaRecon, a startup he founded to commercialize breakthrough technology for tomographic reconstruction developed in his academic research. His research interests include multidimensional and statistical signal processing, inverse problems in imaging, including compressed sensing, computed tomography, and MRI. Yoram currently serves on the editorial board for the Siam Journal of Imaging Science. He is fellow of the IEEE and the AIMBE. His awards include IEEE Signal Processing Society Best Paper Awards, the NSF Presidential Investigator Award, the Technion Fellowship, and the Xerox Senior Award for Faculty Research. So, with that, we can begin.
Thank you very much, Dror, for the kind introduction, and thank you very much, Hamid, for the invitation. It's a pleasure to be here, my first time at NCSU. And it's good to see a good crowd. That means the cookies that are provided are good. This is a picture here of some pictures from our campus of the University of Illinois at Urbana-Champaign. And I was told that with truth in advertising, this is not how we look now. Now the leaves are gone, but this is how we looked a few weeks ago. So still, UIUC is a good place to consider in thinking about possibly a faculty position. We actually are advertising now a few openings. So those of you who are close to graduation may want to consider that. What I want to tell you about today is an approach to sparse modeling. So you might have heard about this before, I'm sure. But we want to look at data-driven sparse modeling. So a lot of modeling is based on engineering principles, engineering models for systems. Now we want to talk about doing everything, or as much as possible, in the data-driven way and see what advantages that prefers. So for me, the motivation for doing that is various imaging problems, medical imaging, other kinds of imaging. Here at the bottom, you see the one-pixel camera in which Dror Baron was involved with at Rice as well. All these problems have in common that often it's difficult to acquire the data. The acquisition is expensive, so you want to reduce the cost of acquiring the data. One way to do that is modeling. And a common model that's being used now is sparsity, but if you model things based on mathematical principles, you don't always get to where you want to go or as far as you want to go. So here's the outline of what I'll talk about. I'll give a brief overview of compressed sensing and sparse representations. How many people know about compressed sensing or some of the main ideas in sparse representation here? Yeah. So everyone, right. Okay, so I'll go very quickly through that.
As imported it.
Okay. So I'll go very quickly through this, but then I want to tell you about some work we've done in using sparse representations for MRI, but the novelty here is doing this adaptively. Then designing the sampling scheme. Again, for compressed sensing MRI, designing it adaptively based on data. And then we'll look at some new ways of adapting sparse models, which we call transform learning or adaptive transforms, which is related to dictionary learning. Those of you who have heard about dictionary learning, it's related, but it's a different flavor, which has certain advantages. Okay, so this is essentially a historical slide, an old slide back from 1999. This slide I presented at a workshop, IEEE Information Theory workshop, and it's really about compressed sensing, except we're not smart enough to come out with that catchy name. We didn't call it compressed sensing. We called it compression on the fly. And as you know, names often are the main sales tools, and we didn't have a good sales tool. So this to a large extent, lay forgotten. But so people think that compressed sensing was invented maybe around 2004, 2005. In fact, as I'll show you, some of this was done back in the 90s. So this is a slide which says the following. You have a sparse object, and you want to do Fourier imaging, so acquiring samples of the Fourier transform of this. One way to do it is to sample the Fourier space densely, reconstruct an image, and then often you'll want to communicate it or to store it somewhere. Then you'll encode it, and then in the end decode it, get back the sparse image. But because it is sparse, you realize that it has limited degrees of freedom, so you should be able to sample sparsely at the outset, and then your compression will be very simple. It will be just scalar quantizer if you want. So you do the compression on the fly in the process of acquiring rather than first acquire and then reconstruct and then compress. So this was our motto here, and we showed how to do this. Here are some experimental results, again from the late 90s. So this is a radar image of the United States. Hard to see much there, but these are, I guess, clouds, formations, some things that reflect more than the rest of the United States. And this is sparse image. So we had an acquisition scheme, which was a sparse acquisition scheme on a pattern like that, which allowed you to reconstruct essentially nearly perfectly with only a small subset of samples taken. So this was, we called it again, our name was 2D spectrum blind sampling. So what's this acronym? 2D is clear. Spectrum blind, you're sampling without knowing the spectrum. So normally with Nyquist type sampling, you have to know the spectrum. You reconstruct based on the support of the spectrum. Here we didn't know the spectrum. You learn the spectrum jointly from sampling the data. So again, it's compressed sensing, two-dimensional compressed sensing. We knew how to do that. We had experimental results. We didn't have the catchy name. So this is, again, this bit of history. So we talk here about an image acquisition system where compression is trivially accomplished by minimally redundant acquisition and so on. So those ideas were there, and they were published and so on, but didn't catch as well. So again, going back to a bit of the history here, back in the mid-90s, we had work on spectrum blind sampling, which is analog compressed sensing. So this was analog compressed sensing done back in the mid-90s with results both for discrete and continuous and analog and all that. So all kinds of results and work jointly with my students here through the 90s. And then in 2000, some information theoretic analysis of the performance of these things. And then only in around 2000, things start being done by other groups which are related. Donohoe and Elad in 2003, rediscovering some of these results and so on. So, and then of course, many important contributions proving very nice theorems about what you can do, but we already had the basis of that before. Okay, so much for theory. Let me go now to the common way compressed sensing is described these days. So you have a vector which is sparse. That's the prior knowledge. You know the vector only has a small number of non-zero elements. You have a matrix which produces measurements. The matrix is fat. That means you have fewer equations than the number of unknowns in the vector. And you don't know which elements are zero, which are not. Can you reconstruct this vector from these limited measurements? So that's the compressed sensing problem. And the answer is yes, if you satisfy some conditions. For example, if this matrix obeys a special property that every s plus 1 columns of A are linearly independent, where s is the number of elements here, then you can do perfect recovery. You can solve this problem P0, which is minimize the number of non-zeros. So this is the L0 norm. It's not a norm, but it counts number of zeros, subject to satisfy the measurement constraints. And that will have a unique solution if you satisfy related conditions. And that's what is called compressed sensing these days. Okay, a bit frozen here. Okay, let's talk now about something related, which is sparse representation. So you have a data vector y. You want to represent it sparsely. So you think about a matrix D and A, which is sparse. So D is a dictionary. And so it's no longer a measurement matrix. In this case, it's a dictionary, but still same idea. You have a sparse vector here. You have y. This time y is given. You're looking to represent it sparsely in terms of linear combination of a small number of elements from the dictionary. Okay, so another way to think of these is atoms. You want to build molecules by combining a small number of atoms. So A is a sparse coefficient vector. D is a dictionary. It can be either square, in which case it may be a basis, or rectangular, in which case it's called overcomplete. And the columns are called atoms, for the reason I described. And then the vector y then belongs to a union of subspaces spanned by subsets of columns of this matrix. Okay, so here's the question. You're given a dictionary, given a vector y. How do you find the sparse representation? Well, it's the same problem as in compressed sensing. Find the sparse vector so that you match the data. Okay, so same problem. One thing about it, it's NP hard, so it's a difficult problem, but there are approximate algorithms which sometimes can be proved to give you the correct solution exactly, or at least something approximate. So there are results about this. Okay, so which dictionaries do you use? So you have data, you'd like to represent it sparsely. Which dictionary should you use? There's a long history of analytical dictionaries. Fourier dictionaries, wavelet dictionaries, curvelet, controllet, you name it. There are various lets, and those allow you to represent various practical signals, images or speech or whatever, as linear combination of small number of elements. So these are analytical dictionaries. They have advantages. They're fast to implement. Many of them are n-log n type algorithms, but in high dimensions, it's hard to design good dictionaries. And often they're designed as separable outer products of one-dimensional dictionaries, and they're not the best you can have. So what can you do? What we're going to look at is adaptive dictionaries. We'll learn the dictionary from the data. Okay? Well, we all know about the kernel-level transform, or PCA, principal component analysis. That's maybe the best known adaptive dictionary. What do? You have data lying here, for example, on these subspace, on these lines. If you run PCA, you'll find indeed this basis vector, which spans part of the data. But then the other basis vector really has nothing to do with the data. It's just orthogonal to the first. So PCA can maybe discover some part of the structure, but it misses a whole lot, misses all the structure. So PCA is not that great. Instead, you can do dictionary learning. You can learn a dictionary adapted to the data. So the idea is this. We have these various vectors y. We want to find a dictionary D so that we can represent all these vectors by different sparse combinations of elements from D. Okay, so that's the dictionary learning problem. You're given a set of training data. Find the D so that you can do this approximation y equal dA with columns of A being sparse. Great. So how do we do this? So here's one popular algorithm. It's called the KSVD. Some of you may have heard about it. So the problem is set up like this. Minimize this difference. So represent your data by a dictionary times collection of sparse vectors, and just solve for this. Optimize over both dictionary and the sparse representation. Turns out this is a difficult problem because it involves two parts. Even if you know D, there is a sparse fitting problem, which is called sparse coding. And then there's also the part of updating D. So the method proposed in KSVD is alternate between these two. And even this part of updating the dictionary, looks like this, died. Not so good. Updating the dictionary, that itself is difficult. It's done in stepwise manner in KSVD. But anyway, it's an algorithm which sort of works. The expensive part here is the sparse coding, solving this approximation problem with sparse elements. Okay, but again, you can solve it using various approximate algorithms, such as OMP, which is a greedy algorithm, which in practice works pretty well. Okay, so we went and looked, how can we apply this to MRI? So MRI, it's this machine, has got a strong magnetic field. You stick your head in there, and turns out they can see what's going on inside. How is that? You magnetize the protons, and then you send a pulse, tip the protons from steady state, and then as they relax, they process and send down signals, and from that you can create an image. So people have looked at using compressed sensing because acquiring the data in MRI is slow. You have to go in K-space, which is the Fourier transform domain, and take samples, and those samples allow you then to reconstruct the image by inverse Fourier transform. So that's a very simple scheme, but then taking those samples takes a long time, and you'd like to speed it up. One is because doctors are greedy. No one a doctor here. Doctors want to make a lot of money, so they want to be able to put many patients through the system. So if you can acquire faster, that's good. But more importantly, you want to acquire dynamic phenomena. You want to acquire the beating heart. You want to acquire the fleeting thoughts, which are manifest as currents in the brain. That takes fast acquisition. MRI cannot do that. How do you overcome that? Well, use compressed sensing. So acquire less data and reconstruct. So there has been work on compressed sensing. And we call that CSMRI, and there is some prior work, and we try to improve on that by learning a dictionary for the data. Okay, so what's the idea in CSMRI? Here's the brain. This is K-space, which is just the Fourier transform of this data. In MRI, you take samples in this space. That's all there is to MRI. And then if you have a sparse transform, such as, for example, a wavelet transform, that means this data is sparse in some sense, so you can try to use that sparsity to take fewer samples. And the idea is to take only partial K-space samples and still recover. If you don't do anything, do simple inversion, you'll get artifacts, but you can do better. And that's what compressed sensing is about. So the problem is set up as these are the Fourier measurements. You have a subset of them. This is the image. This is the available data. So you want to satisfy the measurements subject to making your data sparse with a wavelet transform, for example. Okay, so that's how things are set up. And solving that problem, and maybe in somewhat relaxed fashion, instead of looking at counting number of non-zeros, you look at an L1 norm, so that's a relaxed version, more practical. You also relax the data fit to an L2 norm. This is called total variation relaxed form, and has been done before. So one of the carriers of this banner is Michael Lustig. He has applied it, maybe the first to apply it to MRI in this form in 2007, and there are some improvements on that. But the improvements were not big. People used more sophisticated dictionaries, so wavelets, contourlets, and total variation. So trying to incorporate more and more models for the data, you gain maybe 1.3 dB, not much. The undersampling they achieve is about 2 to 3-fold undersampling. So you can take about 1/3 of the data and receive reasonable images, but not much more. Initially, the promise of compressed sensing was huge. The data is sparse, maybe it's only 5% populated. We should be able to accelerate 20 times. Never happened. So that was a big oversell of compressed sensing for many years, and at this point, people got somewhat skeptical, but still, 2 to 3-fold is not bad, but the question was, can you do better? And our hypothesis was that if you adapt the dictionary to the data, you can do better. So here's how do you learn the dictionary? How do you adapt the dictionary? So we have an image. We look at patches of the image, and we're going to create a dictionary which allows you to represent these patches in a sparse way. So Rij is an operator which extracts a patch from the image. And then we're going to approximate it by the dictionary times a sparse vector. We want to minimize this total deviation in square norm subject to these vectors being sparse. And then you want to minimize over both the sparse representers and the dictionary. So that's the problem. And you can look into how to solve it. So KSVD is one way to solve it, and it gives you this kind of dictionary for patches of an image like the one I showed. So each patch here is an atom, and you'll represent a typical patch as a linear combination of a small subset of these atoms. Okay, the dictionary learning problem itself is again NP-hard, but you can use various approximations, so such as MOD, KSVD, etc., which are essentially heuristics, no proven performance for these, but they sort of work. Okay, how much sparsity do you need? So this is an original brain slice, MR brain slice. This is using only one atom per patch. You pick the right atom, and you get something reasonable, but not that good, 28 dB at PSNR. So the peak signal-to-noise ratio is only 28 dB. If you use more components, you can do better. So the dictionary size is for 8 by 8 patches, so 64 long. So using all 64 elements would be able to represent every patch. But we're able to get very high SNR using only 10 atoms per patch. So you get a factor of 6 in sparsity, or in representation, and you still get very good images. Okay, so that tells you the dictionary is pretty good. Okay, so there has been some such prior work trying to use dictionaries and learning for MRI. What they did, they took a bunch of reference images. So take images from other people, for example, and now you're going to scan yourself. So assume that those images are representative, learn the dictionary of those images, and now use this dictionary for reconstructing the image of a new brain. The improvements are there, but not huge. About 1.6 dB over compressed sensing with wavelets. So these adapted dictionaries sort of work, but not all that much better than wavelets. So the problem, as we see it, is that you learn from reference images, and the reference images are not sufficiently similar to the image you want to reconstruct now. And therefore, learning from those reference images has limited value. So what we did, we looked at, can you learn the dictionary from the image that you're going to acquire, and you're only going to acquire a subset of the samples. So the image will be undersampled. Can you learn the dictionary and do the reconstruction at the same time from that limited data? So we formulated the problem like this. So we have this limited data here. So this FU is only a subset of the Fourier samples. We want to match the data. But then we'll insist that our patches are sparse in some dictionary, which you don't know the dictionary, but they're sparse in some dictionary, and these alpha ij's are sparse. So that's the model here. Again, this problem is NP hard, etc., all these bad things, but we'll use an alternating algorithm, optimizing one thing at a time, which will make this manageable. So there's a dictional learning step. You've seen how this can be done, essentially reducing it to dictional learning. So that's, if you have an estimate of an image, you can learn the dictionary for it. There's a reconstruction update step. Once you have the dictionary, you can solve just minimizing over x. That's a least squares problem. That's an easy problem. And then you alternate between these steps, between learning the dictionary and the sparse representation and updating the reconstruction. So the second problem is a least squares problem. You can solve the normal equations and you can simplify. So it turns out that this can be made in a very efficient way. So really the bulk of the problem is the dictional learning problem. Okay, and turns out that you can actually get this to work. And here are examples. So we look at various sampling schemes. So this is an example of a sampling scheme which is called Cartesian. You acquire lines in k-space, or this is 2D random. You take samples randomly in k-space, and then from this data, we want to learn the dictionary for the data as well as reconstruct. Okay, and this is an example. Here's an original image. If you had all the data and you reconstructed, this will be the image, which looks very good. If you take the difference between the two top images, you see the image on the right, which shows you how much noise there is. So it's noisy data. If you just fill with zeros, you take subsamples by a factor of 5 and put zeros where you didn't have the data, you get the image here on the bottom, which I don't know if you can see from your vantage point, has all kinds of artifacts, and PSNR only 30 dB. On the other hand, if you do compressed sensing with wavelets and total variation, you get a couple of dB, so you do better. But if you take the difference image between this and the original, you see these error patterns. They're essentially aliasing patterns. Because they're undersampling, there's aliasing. Compressed sensing is not able to undo everything. On the other hand, if you learn the dictionary, you gain extra 4 dB, and the error becomes much smaller. So here we show that as the iterations progress, we improve PSNR, 4 dB above dictionary learning. We actually do even better. So 31 is if you had all the samples. We do even better than if you had all the samples. How can that be? So we use only 1/5 of the samples, and yet we get an image with much higher SNR than if you had all the samples. So is there a paradox here? The answer is no. We're using a very strong model for the data. We're using the fact that patches are sparse in some dictionary, an unspecified dictionary, which we'll learn, but that's a very strong constraint. Turns out that allows us essentially to denoise the data, to do better than having all the samples. Okay, so that to us it was actually quite surprising that you can do so well. So again, can show a number of these images. So in all these cases, we can push it pretty far and get good improvements. So in summary, we think that adapting your models to the data can buy you quite a few dB in applications. Yes?
Let me just ask for a clarification here.
Yes.
You're assuming that you have the data
Yes.
in a simulation environment, and you are measuring the data with no noise. Is that right?
No. This simulation is to give us ground truth. So for the simulation we had the data with noise. Or, well, we have noiseless data. We can add noise to it, so we control the noise level. And then we can take a subset of the noisy samples and reconstruct from those. So we learn the dictionary and do the reconstruction from a subset of the noisy samples. And we could compare to reconstruction from the full set of noisy samples. In real application, you would not have all the full data, because if you did, you would not need to take a subset. You just acquire a subset of the data, and then you'd want to reconstruct with that. Okay, any other questions? Please feel free to raise your hand, yell, whatever. Yeah, okay. So, so this is work that has been published last year. Okay, so this is great. What else can we do? So we are learning a model for the data. We're using sparsity. How far or in which direction can you push it? So the other direction we want to explore is, what about the sampling scheme itself? How should you take the samples? So if you read the literature says, distribute the samples randomly. Why randomly? Well, because that's what the gurus said. But there's another reason, because you can prove things. So, those of you who've taken information theory, you know that it's very easy to prove results about information theoretical results about coding and such using random codes. Does anyone use random codes in practice? Not really, but it's a good tool for proofs. In compressed sensing, somehow the theorems have taken over real life. So the theorems are proved using random sampling, and people also use that in real life. And we questioned that paradigm. Why would you need to use random sampling if you could de-randomize it and use something adapted? Yes?
Well, there are actually very good motivations to use random sampling, because if you have IID data, then it's been proved that IID random matrices are optimal from an information theoretic perspective.
Well, they're under certain assumptions. So you need asymptotics pretty much. Otherwise, the constants are useless. Right. So for large, yes. In the limit, random matrices are optimal in the order, not in constants. They're optimal in the order. So you cannot do better. You cannot reduce the order of the scaling laws. You cannot get better scaling laws by anything better than random.
Well, they're optimal also in the constants, but let's take that offline.
Okay, yeah. But anyway, those results require you to go to large, in the limit of large systems. In MR images, the image is 512 by 512. It's far from infinity, and turns out that by tuning things, you can actually do better than using just purely random. Okay, so what are some prior sampling schemes? So, all right, we've seen this slide already about compressed sensing. Here are examples of prior quasi-random schemes. So this is what Lustig advocated, lines with some random spacing. You take more samples at the origin. Why? Because the data has more energy in the origin. Typical images, most of the data energy is near the origin in the Fourier domain, so you take more data there and then spread your samples randomly. Or a random cloud like that, or some various variations on some random sampling. The drawbacks, and what you really usually prescribe is a certain PDF. So you say, let's take the data, use a Gaussian density to distribute the samples with varying density. Okay, but these are ad hoc. There is no particular prescription what's the optimal way or what's a preferable way. Okay, so what we look as, instead of doing a random thing, which has guarantees and good properties, admittedly, but that's for large sensing sampling matrix sizes. What happens if you do some small problem, which is a practical problem? How well can you do there? So we instead focus on designing the sampling scheme in an adaptive way. So what we'll do, we'll take a set of training images, we'll design a good sampling pattern for those, and then use the sampling pattern on some new images. Okay, so what will be the principle of tuning the sampling scheme? Basically, we'll divide the space in which we're sampling into cells. These are the green cells. And we'll consider improving by moving sampling lines or sampling points from one cell to another. So it's kind of a refinement procedure where we'll, a greedy refinement procedure, will move things around to improve our sampling scheme. Okay, so we define a cost function which we want to optimize. And the cost function is this. We're in K-space in the Fourier domain, and that's where we're taking samples. So Yij are the samples in the Fourier domain. J is the index of a test image or a training image. So we have many training images, and then I are the different samples within the training image. Here, so this is the full data. This SM is the sampling operator, which we're looking to adjust, and AJ is some recovery algorithm. So pick your favorite recovery algorithm from sparse samples, and then compare the full data to what you would recover using this recovery algorithm, which essentially fills in the missing data. And then we use some weighting there, which is not essential to discuss here. And we want to minimize, over choice of sampling scheme, the maximum deviation, maximum over all training blocks. So these J will be actually cells within the space in which we're sampling. So if we have multiple training images, there'll be, actually, let me see. No, actually, no. I is the reference. Okay, this is some of the references, and then J are the cells within the reference.
So how do you pick W?
Yeah, W, there is a secret sauce here which tells how to pick it, and I'll put the formula, but it'll take too long to discuss the motivation for that. So it turns out there is some reason to pick a W which is non-uniform, and that has to do with the fact that the energy is non-uniform distributed in the image, in the K-space. So you have to account for that. And give a preference to sampling in places where you have more of the image energy. So
is this particular to MRI because of
this will be, well, no, all images. If you take all natural images, if you take the Fourier transform, they typically have this behavior where near the origin you have more energy, less energy away from the origin. Okay, so I won't go through the details of the algorithm, but the idea is this. We look at these different cells, order them in terms of what's the difference across different cells, and then we'll look at the bad cells where we have large difference because we're looking at the max over all cells, and we'll try to fix the bad cells by putting more sampling point in the bad cells, and the good cells where we already have a good fit, we can remove sampling points from them. So that's kind of a refinement scheme. And basically there's a sequence of moves where if you have a cell in which you achieve good fit, and on the other hand there's another cell in which you have few samples and the fit is bad, you keep moving samples until you meet some thresholds, and you keep cycling like that, and that will essentially equalize it. Those of you familiar with filter design, minimax filter design, where you minimize the maximum deviation of a filter and you end up with an equiripple solution, it's kind of similar. We're minimizing the maximum deviation over all cells, over all of K-space, and that evens out the deviations. Okay, so we have a numerical experiment to show how this works, the methods we use. So this is not restricted to a particular recovery method. We give an example with our adaptive recovery from the first part of the talk, and also compressed sensing a la Lustig, where he uses wavelets. And we show that by adjusting the samples, you can do better. So here's a slice on which we train, and these are some test slices which are different from this. You see the image is different, but it's actually from the same brain, and this is a different cut for a different brain. We'll test our scheme, learn on the top, and test it on the bottom images. Okay, and we start. This is just how the energy is distributed in K-space for that particular image. We start with initial pattern prescribed by just a random distribution, some density prescribed by Lustig. Then after we adjust, we get this. So the final pattern has been modified. I don't know if you can see here. There's some red dots, some blue dots. These are samples which have been removed and moved to another place. So this is modified to here by some movement of some samples. And you can see here, as we iterate over the algorithm, we get an improvement of about, what, 7 dB just by picking a better sampling pattern. You get a huge improvement. And this happens for both our adaptive dictional learning and compressed sensing. Yes?
So you're not changing the number of samples?
No, same number of samples, just relocate them.
So you're
Yes.
iteratively moving them about to
Yes,
achieve a
and,
better...
yeah,
yes.
and we move them about. We trained on a different image from the one on which we're testing. So this is practical. You can learn, say, on images from one brain, then apply it to all subsequent brains, for example, and you will have gain by adjusting your sampling scheme. Okay, so this is, again, some examples and looking at the differences. And we do get these improvements, all these errors that you get with the ad hoc sampling scheme essentially vanish when you optimize your scheme. And we can do this for the various schemes, for Cartesian sampling and other schemes, and in each case we get nice improvements. Okay, there has been work on adjusting the sampling scheme, and the only one we're aware of is by Seeger et al. From 2010. They didn't use, we use directly K-space errors. So we use directly the data to calculate the metric. Seeger used some information gain, so some surrogate, which is an indirect criterion, does not guarantee that you'll actually minimize the errors that you care about. His scheme is sequential at one at a time. We have an iterative scheme. So the optimization scheme is different. Seeger's scheme was tuned to the particular reconstruction scheme of Lustig. Ours will work with any reconstruction scheme that works with sparse data and will adjust you the samples. We get accelerations by a factor of 4 to 6. They were limited up to 2 to 4. So again, an actual improvement in speed up. Okay, so what have we done? We've learned dictionaries adapted to the data. We've learned sampling scheme adapted to the data. What else can we do? Well, the next step would seem to be take this and put it into an MR scanner. Turns out that's difficult. Why? Because there are computational issues. So this learning of dictionaries is a pretty slow process because especially that sparse coding step, finding a sparse representation for a given dictionary, that's still pretty expensive. If you have to do that for a large image, for all patches and so on, it takes a long time, so it's impractical to do this in real time on a scanner. So we looked at a different question. Can you find a different way to do adaptive sparse representations? Okay, so that's our next topic here, which is learning something else, learning sparsifying transforms. So instead of learning adaptive dictionaries, we'll learn sparsifying transforms. So right now in the literature, if you look at adaptive learning for images, there are two models. One is the synthesis model, which is the one I've described so far. Another, more recent, maybe last 2 years, is analysis model. There's a lot of excitement there. And there are these two models. We propose there is yet another one, which we call the transform model. It is really a generalized analysis model, but we'll see that actually it harks back to transform coding, which is older than both of these things, and very classical things, but with a tweak. So again, what is the synthesis model? So that was it. We represent Y with a dictionary D and a sparse vector X, which gives a linear combination of these elements of D. So given D, finding the sparse X is a sparse coding problem, expensive. And you can learn D also using KSVD, but you have to solve many times the sparse coding problem. So that's pretty slow. Also, no convergence results, no guarantees. The analysis problem is somewhat different. It says the following. Let's take Y, apply this transformation in front, omega, and get a sparse result. So now we're saying not that Y itself is sparsely represented, but Y can be operated on to produce a sparse vector. So this is called the analysis model. Turns out the complexity is the same as the synthesis problem, and you also have to solve a sparse coding problem. Okay, what is the transform model? Well, the transform model is something we know, for example, from JPEG compression. What is JPEG compression? You take patches, you take a DCT, and then you say the result is going to be approximately sparse. Let's truncate the small values, throw them out, and that's it. Well, this is really what we're saying here. Y is a patch. Apply transformation to it, maybe a DCT or wavelets. After you apply transformation, you get something sparse plus some residual. And if you throw the residual, you'll be left with a sparse representation. And you can recover Y by taking the pseudo-inverse of this matrix W, multiplying X, and you'll get Y back. So this is essentially the idea of compression. The new twist we're putting here, let's learn W from the data. Instead of this being a DCT or this being wavelets or some fixed transform, let's learn it. Can we learn this? And the question is that going to be any better? Okay, so the sub-problem we have to do is this. Given W, find a sparse vector X such that W, Y minus X is small. We're trying to minimize this eta. So we call this the sparse coding problem. But in this case, it's transform sparse coding. Turns out that this is a very easy problem. Whereas sparse coding was a hard problem, NP hard problem for analysis and synthesis dictionaries, this is a trivial problem. Why? The solution is just take the largest elements of WY, and that'll give you the sparse representation that minimizes the square error. So it's a simple thresholding operation. So trivial, very cheap. So we have eliminated the bottleneck in dictionary learning and sparse representation by rewriting in this form. Okay, so thresholding does the job. Okay, now in terms of how the models are related, we can show the following, that if this is the analysis model, you can generalize it to noisy signal analysis, which admits some deviations, but even more general, there's a transform model. So the transform model is a superset of the previously considered analysis models. It's more general, and conversely, elements in a transform model exist which do not belong to the analysis model. So it's more general, and also turns out easier to work with computationally. Okay, so the summary is this. This is the synthesis model, NP hard. This is the analysis model. Y is some vector plus error, where this vector can be sparsified by transform. And then there is a transform model which says, take the vector Y, apply transform to it, you'll get something sparse plus residual. Looks very similar, but turns out this difference is crucial computationally. Okay, how do we learn it? Okay, so synthesis and analysis are methods, but they're slow, expensive, and no guarantees. They often also, in practice, get stuck in local minima. So you've got to be clever about how you initialize them. Our formulation is in this form. So we have many data vectors Y. Oops. That's a data matrix, which has training set, find a transformation W on the left such that you'll get something which is sparse, approximately sparse. So you minimize this difference. And we call this difference the sparsification error. The difference WY minus X, we call that the sparsification error. That's the residual. We want to make that small. Okay. What do we want from W? Can W be anything? So here is a bad choice for W. One bad choice is make W equal 0. It'll minimize actually this quantity because X equals 0 and W equals 0 is a solution. So it turns out that you have a trivial solution. So that's a bad formulation for the problem because W equals 0 solves it. Well, suppose we prevent W from being 0. That's not enough because W could be made from equal rows. We can take one good row, which multiplied by Y will give you a sparse column, a sparse row, and then just repeat it. And then W doesn't provide much information, just one single row. Can you do better? So we want to eliminate those degeneracies, and the way we do that, we add a log determinant penalty. The determinant will be 0 if you have a repeated row. The determinant will be 0 if W is 0. So any degeneracies will cause the determinant to go to 0, and then negative log determinant will blow up. So if we minimize that, we'll eliminate such things. Turns out if you only do that, the cost will not be bounded from below, and then the minimization problem is not well posed. If you add a penalty on the Frobenius norm squared, the problem becomes well posed, bounded below, and we eliminate those degeneracies. What's more, turns out that with this mu W Frobenius norm, we can control the condition number of W. So we can have perfect control over how well conditioned W is, and that is important in applications. Okay, so that's our problem. The problem is non-convex overall, but we can do alternating minimization, and using this penalty, we can control the condition number, we'll see. Okay, so we have theorems which show that we have perfect control using this combination of lambda and mu. We have perfect control of the condition number. As lambda goes to infinity, if we set lambda equal mu, take lambda to infinity, in the limit we'll have W which has unit conditioning, perfect conditioning. Okay, and also there are still some trivial solutions which are permutations of rho of W and so on, which are equivalent, and we put them in one equivalence class and not worry about them. Okay, so algorithm alternates between optimizing over W and optimizing over X. This is sparse coding. Solve X for fixed W, trivial because just thresholding does it. And then there's a transform update step. X is fixed, sparse matrix, and then optimize over W. We can solve that using conjugate gradients. So that's what we do, and we alternate between the two steps. So in terms of cost, much faster than KSVD. If you look at runtime versus size of the patches, this is KSVD, this is our algorithm, so you get more than an order of magnitude improvement. Runtime versus patch size here. So this is N is patch size, S is sparsity level again. The blue is the new thing. Red is the KSVD. You get 2 orders of magnitude improvement in speed by doing this. And it also works. And not only that, you can initialize in many different ways, and you converge. The cost converges to the same thing. So we overcome, at least empirically, we don't have a proof for that, for global convergence, but at least empirically, we overcome the issue of local minima and initialization, which is sensitive. We converge from very different initializations. We converge to the same cost. Condition number converges to a small number. We get very well conditioned result. And the errors go down and so on. So how do we evaluate the result? One metric is the normalized specification error. We'll see how big is the residual. Ideally, WY will be fully sparse because X is sparse, but there's some residual, and we normalize that. We do better than DCT. DCT has 6.8 specification error. If we learn, we get 4.4. So reduce specification error by learning. We can also look at recovery. So use this dictionary or this transform for compression. You truncate the small coefficients, then you invert to recover. We get a PSNR which can evaluate how good that is. Again, we do better than some fixed transforms. This is how transforms look. And turns out the transforms are different. If we initialize with different initializations, we end up with different transforms. They all, though, have the same cost. So the cost function ends up converging to the same quantity. The transforms themselves are different. Which one should you pick? Probably need additional criteria to give you preference to one transform versus the other. Okay, and then we studied primary effects and so on. Turns out that if you look at this as a compression scheme, you don't want perfectly conditioned transforms. You don't want badly conditioned transform. There is some optimum condition number, and we have that flexibility to do that. Okay, one curiosity. This is a piecewise constant image. What's the best sparsifying transform for it? Well, people would say it's differences. If you take differences, successive differences between pixels in a piecewise constant image, you should get something nearly 0, and that's what you see here. So that works. Can we learn something better? So we looked at the condition number of this transform. It's about 100. We learn transforms with the same sparsity, sparsify just as well. We can get condition number as low as 5 or 6. So much better condition number, same specification by learning. Okay, so all this works, and that's great. Can we do even better? So we've got maybe 5 minutes. Maybe we can do better in 5 minutes. So what's the next step here? We want to look at transforms which are built as a combination. We call them doubly sparse. Okay, so we'll see what that is. So we propose to learn a sparsifying transform as a product of two transforms. One phi, which is a conventional transform. Take that to be wavelets, DCT, your favorite. And then a tweak, a fix, something that improves this transform by pre-multiplying it and make B sparse. So allow B only to have a small number of non-zero elements. So the idea is these analytical transforms are pretty good. Clever people thought about them, came up with good ideas. Let's not throw that out. Let's improve on it. So let's provide a tweak with small number of degrees of freedom to improve the overall transform to make it better. So that's the idea now, and we'll be learning now these modified combined transforms. Okay, so we go back to our formulation, plug in for W, we replace it by B phi. Turns out that log that, you can factorize that. The phi drops out from the equations. You get a reduced problem where you just learn that B, that sparse matrix, and we can put a sparse penalty on B. And the problem is not changed all that much. We can have a similar scheme. Again, it's cheap. It becomes even cheaper because now we have a sparse matrix. You have to do sparse multiplies. That gives you a saving in computation. So I won't go through the detail, but essentially runs much faster. And it works well. So let's see how this works. It converges. And this is an example of the B matrix, the sparse fixed matrix for the Barbara image. And it still gives you a good recovery, good compression with this thing. So we compare different phi. So you can choose that phi matrix from big stuff that you can find in literature. You can use DCT, and you can use Hadamard, you can wavelets. Turns out, actually, I won't go through all the table, but turns out that the performance, if you take DCT and pre-multiply by a sparse learned matrix, or you take Hadamard and pre-multiply by a sparse learned matrix, you get roughly the same PSNR. What's the lesson? The lesson is you can use a pretty crummy transform like the Hadamard, which only involves zeros and 1. It's cheap to apply. And you'll do essentially as well as the DCT, which is more expensive, needs real multiplies, if you allow yourself to learn a sparse matrix. So Hadamard with a sparse pre-multiplier is as good as a DCT with a sparse pre-multiplier. So if you're doing things adaptively, you can use a pretty crummy, still reasonable, pretty crummy non-adaptive transform and refine it using your adaptation. Okay, and then we look here as a function of percentage sparsity. So that B matrix, to operate with it, gets more and more expensive as it gets less sparse. When it's full, it means you really have all degrees of freedom back. So in the case of percentage sparsity equal 10 squared, which is 100, that's the unconstrained case. And you see as you make B more and more sparse, performance degrades. This is the recovery PSNR. Performance degrades, but not much. You can go all the way down to on the order of 1% sparse, so the matrix is almost empty, and it still does quite well. So that tells you that this refinement by a small piece that's learned can do a lot for you. Okay, so I won't go through the plots here. But we can also use this for image compression. We can learn on one image and compress other images, and we've looked at that. We can do image denoising using the scheme, and it works well. Okay, so in summary, we have these adaptive transforms, which now you adapt only a sparse factor, and they work almost as well as an unconstrained transform. Okay, so what's the conclusion from all this? First, having the right model is worth a lot. And certainly with real data, mathematical models are good for mathematics, but they're not necessarily real data do not necessarily want to obey our models, so we better learn those models from the data, let the data tell us what should be the model. And then the somewhat surprising fact, you can learn from single instances. You don't have to learn from a lot of data. You can learn from the image which you want to process. You want to denoise. You want to compress this image. You can learn from this particular image even with limited data. Even with 1/10 of the data from that particular image, you can still learn and do a good job in recovery. And then I guess something which a good motto for school, with the right attitude, learning can be easy and fun, right? So in this case, transform learning provides one way to do this in a way which is easy, and we also hope it's fun. You can get largely reduced cost and still very good performance. So all this work really describes work of one student with me. This is Sai Prasad Ravishankar. Thank you.
Any questions?
Yes, it's a very nice talk. I covered a lot of material. One thing I think you touched on some is that representation. I think this is what you are referring to as right model. Mm-hmm. You touched on Fourier transform, DCA, other things. This might produce
right, and we say that those are not very good models. So we need to learn a model from the data instead of using those fixed operators.
One thing, also we have linear, nonlinear model. So one thing we encountered is that some of the training data we thought is good, but turn out probably is not that as good as we thought.
Yeah, that's a very good point. So if you train on bad data, you'd say, I'll train on the wrong thing, which is not representative of the actual data I'm going to work on later, and therefore it's useless. Yeah, we thought that the training data is good, but then it turned out not to be representative of the data. We say something else. Don't train on training. Your training data should be the data on which you want to work. Don't train on other samples. And we saw that was in the first part where people trained for MR recovery. They trained on other images for which they had full data. They trained on those, and then the recovery of a particular image. They didn't get much improvement. We train on the data on which you want to work. And then the training set, of course, is representative because this is the data. And the surprising fact is you need very little training data to learn, because normally you say I need a lot of training data, therefore I should collect samples which are not the ones I want to work on. Here, train on the data on which you want to work, and you'll still get good results, because we don't worry about over-adapting to the data. The classical motto is in learning is you have to balance overfitting, right, with the generalizability or fitting. So actually, fitting error versus generalizability. Generalizability has to do with overfitting. You don't want to overfit the data because then you'll not generalize well. Here we say, no, don't worry about overfitting. Overfit as much as you can because you're fitting it to the very data on which you want to work. So we remove the question of overfitting. Therefore, we don't have to have a lot of training data because we don't want to generalize in many applications. In some applications, yes, we want to generalize, but in many, we don't want to generalize. We want to work on the particular data set that we have, and we learn from it. So, yeah.
Well, okay. Can you elaborate on that a little bit? Because, you know, I mean, standardly, if you overfit, you fit your data set very well, but then you take a different samples. Now, so how much deviation do you have? You're working on MRI data. If you have, you know, okay, you take a few samples that are representative of the, you know, subjects that you have, but then you would standardly test on a subject that the algorithm has never seen.
So actually, we don't do that. No. We want to image my brain. We take a data for my brain, which is a subset. We take 1/10 of the samples. Okay. So we speed up the acquisition. And now, what do we train on? Well, we train on that particular data, on the data that we're going to reconstruct. On this data, we train and we fit a model to this data, and then we reconstruct it using the model that we learned. So you can think of this kind of as a bootstrap scheme. So we don't use any extraneous data, no other subjects, nothing, just me.
But how does that go into the commercial machine that's going to take about everybody else's heads?
Every person will get a separate dictionary trained for their head. So that's why you need this fast training, because you need to be able, or learning, you need to be able to do that for everyone. Now, the acquisition, where do you acquire? So you have to decide which samples you'll take, because you only take a subset of samples. So you better take a good subset of samples. We can do that. So that was the design part, where we design a good sampling pattern. Turned out that generalizes. So we can learn on other images which samples to take, and we'll take those samples consistently for everyone. At least maybe we'll have a scheme for brain images, another scheme for abdomen, but it seems like this jives well. Then once we've taken the subset of the data, we train a dictionary for that data, and it'll be good only for me. You'll have a different dictionary trained for your brain, etc. So yeah.
About on I guess elaborate on the cost of your training, your fast training algorithms in terms of like your initial goal of real-time implementation.
Yeah. So yeah, it's a good question. So the cost scales. The dominant factor in the transform learning is order n, which is the number of training patches, times n squared. N, small, so big N times small n. Okay, so maybe I can write on this.
Yeah, write on that one.
Big N is the number of training samples. That's number of columns in your Y. And then your patch has n pixels. So if you use an 8x8 patch, this will be 64. And then you square this, and then multiply by the number of training patches. So it turns out that you can get by with a fraction of the patches in an image because images, so we take a random subset of patches, maybe 10, 20% of the patches in the image. So that'll be the big N. And then each patch, so n will be 64 squared. And then it all runs, Sai was running this on a laptop, a dual processor laptop. So all these computations and so on and these images are done on this low-duty machine, and it happens within a minute or so. You can process a reasonable data set. So I think it's very practical to scale it now, certainly with the GPU implementation, to scale it to real-time MRI. Yeah.
So it seems that a lot of our objective function in the optimization problem is non-convex here, right?
Yes.
So I was wondering, first, so if we cannot reach the global minimum, how does that affect the final performance? Since the
Yeah. So you're asking a question, which is a combination of a theoretical question and a practical question. So the theoretical question is, the problem is non-convex. What guarantee can you give it for the results? And the answer is, because it's non-convex, we don't have a result which says that we'll reach the global minimum of the cost function. And then you ask about performance, and I guess what you mean is practical, performance in practice. And as you surely know, performance in practice often has little to do with the theoretical guarantees. If you go to compressed sensing, for L1 relaxation, you get beautiful performance guarantees. But then if you actually go and implement and use a non-convex penalty, things actually work better, and you get better results, but no guarantee. So the two things are not done always going together. But of course, the best of both worlds is to have a theoretical guarantee and good practical performance. So we're looking at variations on this for which we will have convexity and for which we will be able to get a guarantee. Right now, what we can prove is convergence of the cost function, because each of these steps is a decreased step. The cost function is bounded from below, so we can show the cost converges globally. We cannot show yet that the iterates converge. And this is already an improvement of what was done in KSVD, for example, because there the steps are not guaranteed to provide monotone decrease even. So they cannot even claim the convergence of the cost. And in fact, the cost does not converge, and empirically, those other algorithms actually get stuck in local minima and very sensitive to initialization. We empirically tried wild initializations, and it doesn't seem to matter. Yeah.
does that mean that if we rerun the algorithm for the same database as the 2 times, then maybe we can get 2 different bases?
What we found is, and actually I showed, that if you initialize differently, you get two different transforms, but the cost is the same. So they achieve the same. So what we conjecture is there are multiple global minimizers, and empirically at least we seem to be reaching each time a global minimizer, because the cost ends up the same place, but the transform itself is different. So from the perspective of the cost function, if we like the cost function as our performance metric, we're getting the same cost each time. But yeah, there's more theoretical work to be done here, absolutely.
Do you
expect this to generalize to other imagery like radar or sonar?
So I think that would have to be tested. I think some radar imagery is very sparse itself, even without dictionaries. So if you look at SAR images, returns from corners and such things, so you have already sharp features, but I think with a dictionary or a transform, you even get greater sparsity. So that will allow you to do compressed sensing acquisition with greater acceleration factors. So I think similar things could be done. And certainly the transform formulation is in some ways equivalent to the dictionary formulation, but it's just computationally more effective. So I think it should be effective for there as well.
Okay, well, let's thank our speaker again.
Thank you.